probability of clinical recurrence, and so at 3-year mark it's about what, 55% or something. So that's a pretty high number. So that's supposed to be useful information to help make a decision from. Okay, so here's another picture. So this is a patient who has PSA comes down and stays down, projected to stay down, and so this person has basically no chance of recurrence according to this model. So it reacts to the pattern of PSA is the point here. And here's one where there's very little follow-up, less than 1 year follow-up. We really don't know what's going to happen in the future, and so that gets reflected in those curves. Probability of recurrence for this particular patient is still 13% because they might have had bad baseline characteristics or something. So that was all if that patient was in the data set, because I'm actually grabbing stuff I've saved for the random effects for patient-specific information. But new patient, Mr. Smith, isn't going to be in the data set, and I wouldn't know if he was, too. So what we have to do there is sort of have a scheme which calculates the probability of recurrence for a new patient. So it's the same method as before, those sums and integrals. I have some things saved from the training data set, the sort of population parameters for gammas and omegas, but I have to create the random effects for that person's data. So I basically got to fit a model to the new person's data, just their data, to get the random effects. So there's this website, and to get this prediction, you basically run a quick Markov chain Monte Carlo, a quick analysis of that one person's data, informed by what you've learned from the training data for population parameters, and just have to estimate 3 things for that one person: a starting point, my drop, and my rate of increase. So this is live. Anyone can go to this. There's some number of users. It's not as many as I'd like, but so you're a patient, you're a healthcare provider. You get to enter information about you, your Gleason grade, your T stage. So enter what PSA was, baseline PSA. Okay, so you have to enter this data about you. You enter dose of radiation, you enter in this box here the whole pattern of PSA. You have to know, there's a date when radiation entered, so there's a little data entry. There's a little data entry. There's also a box down here. If you've saved your data on your own computer, you can update it and do it again. So I put in, automatically got some data in there. So you see this pattern, right? PSA. Person was treated in 1999 and they've had 4 values, last one 2007. So there's a button here which says calculate. So that's going to do this quick calculation, not going to take 12 hours. It's going to take 3 seconds probably. And it's going to produce a couple of curves. So this is the data we entered, the pluses, and the projected PSA values in the future, which is right. And the real thing is here. So don't worry about the red region. There's a line in the middle here, which says about 20% for the predicted probability of recurrence for that patient. So that's the essence of what you get. So that 20% is supposed to be useful. That's the idea here. And if I changed that last value in 2007 to 12, say, right, that would be a high value. Hopefully, it's going to respond and say, "Whoa, this isn't looking so good." Still, they don't have a clinical recurrence. So you press calculate. Well, something else happened here too. So it came up with some warnings that said, your data doesn't really look like the data we've seen, but we've built it on. So there's a lot of little checks in there to sort of make sure people aren't as inputting or warning them when they put in what we think isn't very reliable data. So that was, and then you can see the probability of recurrence went up a lot, as you'd expect. So I put in 12, so we change that to, it'll detect other things too. So I put in a bad value in the middle there. But you never see data like that. So that's an outlier, so I'm hoping it'll detect it. Yeah, so there's some red print showed up. Right, and it doesn't look like it fits very well, right? The top curve. And somehow it thought that was now a less chance of recurrence. So here's a quiz question. Is anyone here a prostate cancer physician? No one's owning up anyway. So there's 8.5 was the original PSA. So I made that 28.5. So that person looked worse coming in. What do you think? Do you think the risk's going to look higher or better? So you could say it might look better because they've come down a long way and stayed down. Or it might look worse because they've started off worse. In fact, it's going to look a little better. The treatment sort of seemed to work for them. So it didn't change that much, but it changes a little bit less. So there's websites out there, and so there's sort of issues with this, what to present exactly. So working with people who specialize in health communication a little bit, and they're sort of disgusted with my version of what was a helpful graph. They say, majority of patients aren't really going to get sort of the information the way you've conveyed it in terms of risk. Even they might not even be able to understand risk, but they certainly won't understand the graphs. And so the sort of preferred method by some people anyway is to draw 100 faces and colour 22 of them one colour and 78 another colour, as sort of a way to convey information which is broadly understood and understood correctly. So there's sort of those type of issues and what to present and how to convey it. This is going to be challenging for any patient to do themselves because they're not going to know their Gleason grade from their biopsy in 2003. So this is really for the healthcare provider to have that. Needs to run fast, it does. It's an aid to decision making. So the predictions I'm giving you are probability of recurrence if you don't do anything, if you don't take hormone therapy. But I could also add, or we haven't worked that up yet, what if you started hormone therapy today? And those predictions would be a lot less. And there's sort of issues of how to publicize it, and if we want to. And validation, I'm not sure how much time I've got here, but so what are the uses? One is I've sort of focused on the patient monitoring use. Another thing would be an entry criteria to a study. If that probability was bigger than 10%, somehow it's eligible for a sort of a new agent which you're interested in investigating how effective it is. You want people who are at higher risk for recurrence in those sort of studies. Okay, so what do I got? About 5 minutes. So there's validation, it's somewhat, well, it wasn't easy to build, but you can build these sort of models, but they may need some confidence. Okay, so there's validation. I've got training data, I got validation data, and it's a little trickier than usual. I'm predicting an event in a short period of time, but it may not happen at all. So the data I have to validate on is also censored data. So it's a little more complicated than standard validation. And so the approach I'm taking is just a graphical approach. So just stepping back a little, pretend I had a binary outcome, yes, no. And I make a predicted probability, call that p hat for patient I. This Hosmer-Lemmerschau way of validating is to take all the people who I predict similar probabilities. So everyone who I say 20% predicted probability, or about 20%, group them together, and then look at, maybe there's 100 people like that, see if what happens in the future for those 100 people is at about 20%. And that would be then valid. So that's sort of the style we're doing here. And do that for people who have 10% predicted probability and do 10 out of 100, get the event. So that's Hosmer-Lemmerschau. So another, just as a side here, another very standard way that people use to validate models is ROC curves, look at area under the curve. So there's a sort of a problem with this, because if I have a predicted probability for somebody, for lots of people, I just divide all those by 2. So what used to be 20% now becomes 10%. I get exactly the same area under the curve for an ROC curve. So the ROC curve is not good at saying I've got a predicted probability right. It's good at sort of ranking people, but it's not good at assessing whether a predicted probability is correct. Okay, so for the data I have, I'm predicting a survival distribution, a curve. Basically, going to group people together who have similar curves and then see what happens to them in the future. And does it match what I predict? So I'm going to compare the group of people who have similar curves with what actually happened to those curves, with what happened to those people. And so this sort of formally what we did was we built a model on a training data set, which was 2,400 patients from 3 different cohorts. And then we're going to actually do a prediction on the training data, so that should look pretty good. And then we're going to do a prediction on these other data sets, one from Vancouver and one from Melbourne. And so here's the grouping. I'm going to look at, just for illustration, people who've made it to 3 years. So they're still at risk at 3 years. You know their history of PSA. What's the chance of recurrence within a future 3 years? So that's sort of a metric, of a way to group people. And that could either be less than 2.5%, between 2.5 and 10, between 10 and 30, or bigger than 30. So 4 groups who are supposed to be similar according to the model. I'm going to make, then I'm going to look at those four groups and say, well, give them the data up to 3 years, what happened to those after 3 years, and draw Kaplan-Meier plots. So this is the model reapplied to the training data. So there's these 4 groups who are supposed to be sort of lowest risk, up to the biggest risk, from 3 years out into the future, and I was trying to get these probabilities at 6 years, right, 3 years into the future, to be, so the black curve should be between 0 and 2.5%, so it's about right. So these, this is the order, black, red, green, blue, so that's preserved in the predictions. And so this green group, for example, should be around 20%. I predicted 20%, and do 20% of them get the event. So the green group at 6 years is somewhere around 0.8, so it's about right. So that was good. So this is the data from Vancouver. So this is now an external data set. Not quite as good, but not bad. Still got the correct order. Probabilities are about right. And then this is what, if you go to Melbourne to get treated, you do way better. So I don't know what that says. So this doesn't look on the surface like it's working at all. We're getting too high probabilities. People aren't getting as many recurrences as we predicted. So the guys in Melbourne, they don't count local recurrence. They only count distant metastases. So they weren't counting some subset of recurrences we were, maybe correctly so, but that was sort of to be expected in some sense. So just a couple of last slides. So this was a big model, and is it worth the trouble? You could envision some somewhat simpler ways to do this. And the key is, if you just use baseline variables, it's not going to be as good. But there might be other ways of using recurrent PSA, which are basically almost as good. And we could extend the model. We could include race as another baseline variable. We could also calculate probability of recurrence if you started hormone therapy. Ideally, we'd like to sort of not pool together local and distant recurrences because they have quite different implications in terms of a seriousness. We could also build models for many patients get hormone therapy at the same time they get radiation therapy. So we could build models for that setting as well. And a number of references here, and a number of people who have been involved here, some colleagues, postdocs, students, clinicians, and web-based folks. So thank you very much.